Okay, so let's look at this question. There was a hint, or not a hint, a thing here that says observe you need both sines and cosines. So that's a little confusing. What I should have said is that the g of t function, or sorry, the b of t function, the a of t function, like these guys up here, uh, like those guys right there, the bk of t, those will be have both sines and cosines, unlike before where it was an exponential function. So we're going to look and we see, okay, the boundary conditions are on the function itself, not the derivative. U of 0t is equal to u of pi t. Those are both equal to 0. What this tells us is that the eigenfunction, well, the basis that we want to expand the solution in is going to be the sine basis, because the sine basis is the thing that satisfies the boundary conditions. So how do we know whether or not we want to use a cosine basis like we have up here, or a sine basis like we have up here? It's going to be whichever one satisfies the boundary condition. So remember when we do separation of variables, so this is based on separation of variables. It's kind of like a shortcut. But when we did separation of variables, we had the equation in the x variable, and sine satisfied that equation when we had the function itself was equal to 0 at the endpoints, but cosine satisfied the boundary condition when we knew that the derivative of the function was equal to 0 at the endpoints. So we come down here. We want whatever function that we're going. So in principle, you could pick any basis. You could pick the sine basis or the cosine basis to write the solution in, but it's not going to satisfy the boundary conditions. It would just satisfy the PDE and the initial condition. But whatever your basis functions are, those basis functions need to satisfy the boundary condition. And it's sine that satisfies the boundary condition, or sorry, yeah, it's sine that satisfies the boundary condition, not cosine. So we assume that u of xt can be written as a sum, and I'm just going to write k greater than or equal to 0 here instead of k equals 0 to infinity. Sorry, 1. Well, I'll just do k equals 1 to infinity. Sorry. You get to see game time decisions here. And I'm just going to call it for now ck, oops, yeah, I'll call it for now ck of t, lowercase k, ck of t sine kx. Okay, and we're going to plug this into the PDE. So plug this into the PDE to get, okay, this is very similar to what we have above. Okay, on the left-hand side, when I take the derivative on the left-hand side, the derivative is only going to fall on the ck's. The t derivative is only going to fall on the ck's because as far as t is concerned, x is a constant. So this will be ck prime of t sine kx, and then when I take the derivative on the right-hand side, it's only going to go on the sine. And so this is why we like to use the sine basis, because when I take two derivatives on sine, I'm going to get a multiple of sine back. So this is ck prime of t. The double derivative of sine is minus k squared sine kx. Okay, you do one derivative, you get k cosine kx. You do another derivative, you get minus k sine kx, which is minus k squared. Okay, so now if we rearrange, so subtracting as above, we get, so 0 is equal to the sum, k equals 1 to infinity, and we're going to have, oh, sorry, there's a double prime. This is a double prime here. This is going to be ck double prime of t plus k squared plus k squared sine k squared. What am I doing here? That there's not a prime there. Good gosh, dude. All right, ck of t sine kx, and this implies. Okay, so why does it imply that? Well, we saw that the sine x, the sine functions are orthogonal, meaning they're linearly independent. So it's kind of like a polynomial. If you think back to polynomials, two polynomials are equal if and only if the corresponding coefficients are equal. A similar thing is true here. Two sine series are equal if and only if the corresponding coefficients on the sine are equal to 0. And so this tells us that ck double prime of t is equal to minus k squared ck of t. Oops. Okay, so this is now a second order differential equation in the t variable. It's minus k squared is positive, so minus k squared is negative. So the general solution is going to be ck of t is equal to ak cosine kt plus bk sine kt. And if you're wondering where this comes from, just look it up. This is solving a second order differential equation, so it's something that I expect that you know how to do. Okay, so now what we're going to look at is we need to figure out what ak and bk are. But now as above, we're going to use our initial conditions here. But notice I have a t derivative on one of my initial conditions. So first I'm going to take a derivative of u. So we need to use the initial conditions. So we'll first take a derivative. Okay, so actually let me just summarize what we have here. So therefore, let's write out what the solution is. So therefore, u of xt is going to be equal, so where do we have the sum? So it's going to be right here. And I have a formula for what ck is. Ck is this right here. Put that in brackets just so it stands out. Oh, thank you. Okay, so now we need to use the initial condition. So we're going to take a derivative, and notice it's a derivative in the t variable. So the t derivative of u of xt, whoops, is going to be equal to, and I'll just reuse this and hope I don't make a typo. Okay, so what we're going to have when I take a t derivative, when you take a t derivative of the cosine term, this is going to be equal to minus k sine of kt. I don't know why I deleted the k, like I had to delete the k to move it to the outside. Anyways, that was dumb. Okay, and over here we're going to have k, I did it again, why am I doing that? It's going to be k times cosine. Okay, and so now to use the initial conditions, bringing in the initial conditions. Okay, if I look at u of x0, I know this is equal to f of x by what's given. Let me write it like this. I know f of x is equal to u of x by what's given, and then by the work that we've just done, I know this is equal to, okay, so I'm going to look at, this is the sum here. This is what u of xt is. And when I plug in t is equal to 0, notice this term goes away. And because sine of kt is 0, so that goes away. And notice cosine of kt is 1, so that goes away. And so we're just left with ak. So we've seen this before many times, and we know that ak is equal to the frac 2 over pi, 2 over pi times the integral from 0 to pi of the initial function. I'm going to use the y variable because I want to use the y variable because I don't ever want this to be confused with the x variable that's right here. I know I did it in class where I had this a couple of times where I had f of x sine of kx, but I should have done it with f of y just because I want there to be a dummy variable here, just so we're not going to confuse it with the x in the solution. Okay, so sine ky dy. Okay, so that's what ak is. For the bk we're going to use the derivative. So for the bk we use, it's going to be very similar. So this part, like at this point, we've done this part in class several times, the finding the coefficients. That's all we're doing now. So we've got g of x is equal to the t derivative of u evaluated at x0. Okay, but where is the t derivative of u? Where did I put it? right here. This is the t derivative of u. So let me copy it down here. Okay, so now what's going to happen? Well, that term's going to be equal to 0 because sine of 0 is 0. What is bk, or sorry, what is the cosine term? That's going to be 1 because cosine of 0 is 1. I just deleted the k. There was a k here that I deleted, right? Yeah. That k there, I deleted. That's going to be important. Okay. So now, what are we doing? We're writing g of x as a sine series, and the coefficients are going to be k, bk. Okay, so this means that k, bk is equal to this integral, the integral from 0, pi of g of y sine ky. Let me compile this so we can look at it. Okay, I should have done that before. I'm sorry. So that's what we have here. K bk is equal to that. But we don't care about k bk, we care about bk. So that is bk, and I'm just going to copy and paste this again. K bk is equal to this, but now I'm dividing both sides by k, so there's going to be a k down here as well, and that's it. Okay, so what are we doing here for this problem? Well, let me go back up even to one of the easier problems. So we know, not one of those. Let's look at this one. So we've seen this problem before, okay, and we've already solved this problem, but I want to introduce a different perspective just because it's going to be helpful when we look at more general problems later on. But the idea is, I haven't proven it, but I've told you that it's true, and we'll talk about it next week, but I know that I can expand any function in the x variable as a sine function, sine of kx, with these coefficients. Now, if it's also a function of t, these coefficients are going to change depending on what t is. So these coefficients are actually a function of t. And so now what I'm going to do is I'm going to take this solution. I know that in principle I can do this for every value of x, or sorry, for every fixed value of t. I can write the solution as an infinite series of the sine functions. And as t changes, I'm going to get a different coefficient here. So I can take this, I can plug it into the PDE. That's what I've done here. And I get bk prime sine of kx on the left-hand side, and this is what I get on the right-hand side. I'm going to subtract the right-hand side from the left-hand side, and I get this. The only way these two functions can be equal to 0, the only way, like if I have a polynomial that's equal to 0, the only way a polynomial can be equal to 0 for every value of x is if all the coefficients are 0. So the only way this function can be equal to 0 for every value of x, the only way this function, this function there can be equal to 0 for every value of x is if all the coefficients are equal to 0. Okay, so this tells me that bk prime plus k squared bk is equal to 0. That's this differential equation. I solved that differential equation for bk. I get this guy right here. And now this tells me that u of xt, or g of x, can be written like this. And I find the coefficients just like I did in class. And so we've done the exact same thing down here. Well, not exact same because it's a second order equation, the t variable as well. But now our equations, our differential equation for ck is a second order equation rather than a first order equation, but the general outline is the same. We're going to say I know that I can write my solution as a sequence of sine functions. Now in principle, as we'll see, I always know I can write my solution as a series of sine or cosine functions, but I don't know what it's going to, like the boundary is kind of up for grabs. The boundary is always going to be like, I don't know if I can actually make this work at the boundary or not. So because of that, I need to be careful that I pick basis functions that are going to satisfy the boundary conditions. So in principle, like there's a sense in which I could have used cosine kx here, and it would have satisfied everything here except for the boundary condition. But it's a boundary value problem, so the boundary condition is kind of important here. So we want to make sure that we pick basis functions that satisfy the boundary conditions. And that's why we picked for this problem, that's why we picked cosine functions. Because if I take the derivative of cosine, I get sine, and those are going to be 0 at the boundary points. But sine, if we take the derivative of sine, you get cosine, and those will not be equal to 0 at the boundary points there. Okay, so that's all for this problem.